You were taught that quantum tunneling is one of the great solved problems of physics. Particle hits a barrier it does not have the energy to cross, and yet somehow it appears on the other side. Weird, yes. Counterintuitive, absolutely. But understood. Settled science. You probably learnt about it in a physics course, or from one of the dozen YouTube videos that use the same analogy about a ball rolling through a hill. And every one of those sources told you the same thing. Tunneling works. We know why. And it is one of the triumphs of quantum mechanics. That is not the full story. Not even close. In 1928, when George Gamow first described quantum tunneling mathematically to explain how alpha particles escape atomic nuclei, his equations contained a property that nobody wanted to examine. A question buried in the math itself. How long does tunneling take? How much time does the particle spend inside the barrier? That sounds like the simplest possible follow-up question you could ask. You just told me a particle passes through a wall. Okay, how long is it inside the wall? A child would ask that. And when a physicist named MacColl finally calculated the answer in 1932, 4 years after Gamow's breakthrough, the result was approximately 0. The particle appeared to spend no time inside the barrier at all, as if it skipped through space without passing through the space in between. The physics community's response to this was silence. 30 years of it. From 1932 to 1962, nobody published a serious follow-up on the tunneling time question. Not because the question was trivial, because the answer was terrifying. A traversal time of 0 implies infinite velocity. Infinite velocity breaks special relativity, and special relativity is not optional. It is the load-bearing wall of modern physics. When the question was finally forced back open in 1962, the results were worse than MacColl's. The new analysis showed that the tunneling time does not just approach 0, it becomes independent of barrier width. Make the barrier a meter thick, make it a kilometer thick, make it a light year thick. The math says the particle crosses it in the same amount of time, which means for sufficiently thick barriers, the implied velocity exceeds the speed of light, not by a little, by as much as you want. That result has now been confirmed experimentally in every wave system ever tested. Microwaves, single photons, ultra-cold atoms, and here is the part that should genuinely disturb you. As of right now, nearly a century after tunneling was discovered, there is no consensus on what tunneling time even means. Physicists have proposed at least 10 mutually incompatible definitions. They do not agree with each other. They do not converge on an answer. And when the most precise measurement of tunneling time ever performed was published in Nature in 2020, it did not resolve the question. It made it worse. Lower energy particles spent less time inside the barrier, the opposite of every classical intuition. And the answer contradicted a completely different tunneling time measurement published in Nature just 1 year earlier by a different group using a different method. The property that was discovered in 1928, the property whose implications were quietly shelved before anyone had to confront what they meant, is not some obscure footnote in the history of quantum mechanics. It is a crack in the foundation. And the crack runs through everything, through the nuclear fusion that powers every star in the sky, through the mutations in your DNA that may be driving both evolution and cancer at this very moment, through the event horizons of black holes, through the stability of the vacuum itself, the ground state of reality that everything you have ever known sits on top of. You were never told any of this. And the reason you were never told is not that it is speculative or fringe or uncertain. The data has been sitting there for 97 years. Nobody wanted to look at what it actually means. So let me take you back to where this started, because the story of how this question was born, buried, and eventually forced back into the light involves some of the strangest characters in the history of physics. A man who tried to escape the Soviet Union in a kayak, another man who was destroyed by the same McCarthy witch hunts that targeted Oppenheimer, and a third man who lived to 101 and never got credit for any of it. In the summer of 1928, a 24-year-old Ukrainian physicist named George Gamow arrived in Göttingen, Germany, to work with Max Born. Gamow was physically enormous, well over 6 feet, with pale blonde hair and eyes that his colleagues described as startlingly blue. He spoke German with what one physicist called a very picturesque accent, which is a polite way of saying it was nearly incomprehensible. He drew cartoons on his physics papers. He had a sense of humor that ranged from playful to genuinely absurd. He once wrote an academic paper with his student Ralph Alpher and convinced Hans Bethe to add his name purely so the author list would read Alpha, Beta, Gamow, a pun on the first 3 letters of the Greek alphabet. This was a man who published foundational contributions to nuclear physics and cosmology, while also writing children's books about a character named Mr. Tompkins, who shrinks to quantum scales. He was not a typical physicist. He was a force of nature who happened to do physics, and in the summer of 1928, he was about to solve a problem that had stumped everyone for 17 years. The problem was this. Since Rutherford's scattering experiments had revealed the structure of the atom, there was a number that made no sense. The Coulomb barrier of a uranium nucleus, the energy wall created by the electrical repulsion between the positively charged alpha particle and the positively charged remaining nucleus, was at least 8.5 million electron volts high. But the alpha particles that uranium actually emitted carried only about 4.2 million electron volts of kinetic energy, less than half the barrier height. To put this in terms you can feel, imagine you are standing at the bottom of a cliff that is 100 meters tall. You have a cannon that can launch a ball 50 meters into the air, not even close to the top. And yet somehow, unpredictably, some of those cannonballs appear on the other side of the cliff, not over it, through it. That was the alpha decay problem in 1928, and every solution that classical physics could offer was somewhere between desperate and embarrassing. Rutherford himself had proposed that alpha particles might temporarily capture 2 electrons, become electrically neutral, sneak past the Coulomb barrier without feeling the electromagnetic repulsion, and then shed the electrons once they were clear. Even by the standards of early nuclear physics, this was an ad hoc explanation held together with hope and baling wire. Gamow recognized the answer lay in the new wave mechanics that Schrödinger had developed just 2 years earlier. A quantum wave function does not stop abruptly at a potential barrier the way a classical ball stops at a wall. The wave function decays exponentially inside the barrier, but it does not drop to 0. If the barrier is finite in width, and all real physical barriers are, there is always a non-zero amplitude on the far side. There is always some probability, however small, that the particle will be found beyond the barrier. As Gamow later recalled, "Before I closed the magazine, I knew what actually happened." He submitted his paper to Zeitschrift für Physik on July 29, 1928. The math was elegant and devastating in its explanatory power. The tunneling probability takes the form of an exponential function that depends on the integral of the square root of the energy deficit across the entire barrier region. This is the Gamow factor, and it explains something that had baffled every living physicist. It explained why uranium-238, with its alpha energy of 4.27 million electron volts, has a half-life of 4.5 billion years, while polonium-212, with an alpha energy of 8.78 million electron volts, decays in 0.3 microseconds. Roughly double the energy, and the half-life changes by a factor of 10 to the 28th power. That is a 1, followed by 28 zeros. If you tried to count from 1 to 10 to the 28th, counting one number per second, it would take you longer than the current age of the universe. Longer, in fact, than the time remaining before the last stars burn out and the cosmos goes dark. That is the sensitivity of tunneling probability to energy, and Gamow derived it from Schrödinger's equation at the age of 24. It is, to this day, one of the most dramatic quantitative relationships in all of physics, and it fell out of the math so cleanly that Gamow apparently derived it in a single sitting. Here is where the story takes its first uncanny turn. On July 30th, one day after Gamow submitted his paper, two physicists at Princeton, Ronald Gurney and Edward Condon, independently submitted their own solution to the exact same problem. They sent it to Nature. Neither team knew about the other's work. They had been attacked by the same puzzle, reached for the same tools, and arrived at the same answer within 24 hours of each other. This kind of near-simultaneous discovery is not unprecedented in physics. Newton and Leibniz with calculus, Darwin and Wallace with natural selection. But the tunneling case is especially striking because of how specific the problem was and how short the window of overlap. Gurney and Condon's paper contained a line that I personally think is the most beautiful sentence ever written in a nuclear physics publication. Much has been written of the explosive violence with which the alpha particle is hurled from its place in the nucleus. But from the process pictured above, one would rather say that the alpha particle slips away almost unnoticed. Slips away almost unnoticed. Remember that phrase. It is going to take on a meaning that Gurney and Condon never intended, and it is going to haunt the rest of this story. Now, there is someone who got overlooked in all this excitement, and I want to give him his moment, because what happened to him is part of the pattern. Friedrich Hund, a German physicist working in Göttingen, had actually described quantum tunneling mathematically a full year earlier, in 1927. Hund solved the Schrödinger equation for a symmetric double well potential and showed that a particle in one well could tunnel to the other well with a calculable frequency. His tunneling was between bound states in molecules, not the continuum tunneling of alpha decay, but the underlying physics was identical. He had identified the tunnel effect before anyone else. He received almost no credit for it during his lifetime. His colleague Robert Mulliken, who won the 1966 Nobel Prize in Chemistry for molecular orbital theory, built substantially on Hund's work, always maintained he should have shared the prize. The Nobel Committee disagreed. Hund lived to 101 years old, dying in 1997. He watched the discovery he made first be attributed to others for 7 decades. I bring this up not just as historical trivia, but because Hund's erasure is the first instance of a pattern you will see repeated throughout this story. The tunneling phenomenon and the people associated with it share a strange tendency toward being overlooked, shelved, and quietly forgotten. The physics world celebrated the tunneling papers for exactly the right reasons. The model reproduced the empirical Geiger-Nuttall law of 1911 from first principles. It was the first successful application of quantum mechanics to nuclear physics, and it did something philosophically enormous that gets glossed over in textbook accounts. It decisively vindicated the probabilistic interpretation of the wave function at exactly the moment when Einstein and Schrödinger were still fighting against it. If tunneling works, if particles genuinely have a probability of appearing where they classically cannot be, then Born's probability interpretation describes something real about the physical world. Eugen Merzbacher later wrote that the tortured theories explaining alpha decay vanished almost overnight. But here is what nobody said. The same mathematics that solved alpha decay also opened a question that was arguably more disturbing than the one it closed. Because the moment you accept that a particle tunnels through a barrier, you are forced to confront a deceptively simple follow-up. How long was it inside? 4 years passed before anyone looked seriously at this question. In 1932, a physicist named L.A. MacColl published a paper in Physical Review titled Note on the Transmission and Reflection of Wave Packets by Potential Barriers. What MacColl did was straightforward. Instead of treating the tunneling particle as a stationary wave, a mathematical abstraction that exists everywhere at once, he modeled it as a wave packet, a localized pulse of probability moving through space like an actual particle would. He tracked when the peak of the incident packet arrived at one side of the barrier and when the peak of the transmitted packet appeared on the other side. His conclusion was stark. The transmitted packet appears at the far side of the barrier at about the same time that the incident packet reaches the near side. There is no appreciable delay in the transmission of the packet through the barrier. I want you to sit with that for a moment. Not a small delay. Not a delay that is too fast to measure with existing technology. No appreciable delay at all. The particle appears on the far side of the barrier at essentially the instant it arrives at the near side, as if the space inside the barrier, the physical distance between point A and point B, simply did not exist for the tunneling particle. As if it took a shortcut not through the barrier, but around space itself. And here is where I need you to understand something about the culture of theoretical physics in the early 1930s. Because what happened next, or rather, what did not happen, is the beginning of the most sustained act of collective avoidance in the history of modern science. Nobody followed up. I spent a genuinely unreasonable amount of time, hours that I will never get back, going through the citation records of MacColl's 1932 paper, looking for any published response in the years immediately following it, any criticism, any attempt to replicate or extend the analysis, any theoretical exploration of what a zero transit time actually implies for our understanding of space and velocity and causality. There is essentially nothing for 30 years. The physics community read the result, recognized that it implied something they could not reconcile with special relativity, and moved on. Not loudly, not with a debate or a controversy or a series of heated letters to editors. They just quietly stopped thinking about it, put it in a drawer, closed the drawer, and walked away. Ephraim Steinberg, the physicist who would eventually make the first definitive measurement of tunneling time 88 years later, described the psychology of this perfectly. When you get an answer you cannot make sense of, you do not publish it. You put it in a drawer and hope someone else deals with it. That is not a description of how science is supposed to work. That is a description of how it actually works when the answer threatens something fundamental. A 2022 review published in the European Journal for Philosophy of Science confirmed what the silence implied. The tunneling time problem, the authors wrote, then lay low for several decades. 3 decades of lying low. And during those 3 decades, physics was not exactly idle. The field split the atom, built nuclear weapons and nuclear reactors, discovered the transistor that would create the computer revolution, formulated quantum electrodynamics to 11 decimal places of accuracy, and began constructing the standard model that describes every known fundamental particle. All of that happened while a question about the most basic temporal property of quantum tunneling, the first and most celebrated prediction of quantum mechanics applied to nuclear physics, sat undisturbed in a drawer in LA MacColl's filing cabinet. The silence was broken in 1962, and the person who broke it was not even an academic physicist. Thomas Hartman was a semiconductor engineer at Texas Instruments. He was not interested in the philosophical foundations of quantum mechanics. He was not thinking about what MacColl's result meant for special relativity or for the nature of time. He was interested in something much more practical. He needed to understand the frequency limitations of thin-film electronic devices. Specifically, the metal-insulator metal junctions where electrons tunnel through an insulating layer. He needed to know how fast electronic signals could propagate through these barriers for practical engineering reasons. So in 1962, Hartman sat down and did the calculation that academic physics had been avoiding for 30 years. What he found was not just a confirmation of MacColl's result, it was categorically worse. Using the method of stationary phase, a standard mathematical technique for analyzing the propagation of wave packets, Hartman derived the group delay for a quantum particle tunneling through a rectangular potential barrier. The group delay is essentially the time difference between when the peak of the incoming wave arrives at the front edge of the barrier and when the peak of the outgoing wave appears at the back edge. For very thin barriers, the delay is small but finite. As you make the barrier a bit thicker, the delay increases slightly. But then, something extraordinary happens. The delay reaches a maximum value and stops growing. It saturates. It hits a ceiling and stays there. From that point on, no matter how much thicker you make the barrier, the group delay remains the same. A barrier 1 nanometer thick, and a barrier 1 meter thick, and a barrier 1 kilometer thick all produce the same group delay. This is the Hartman effect, and when you sit down and trace out what it implies, it breaks something that should not be breakable. If the time is constant and the barrier width is growing, the effective velocity, which is simply distance divided by time, grows without limit. For sufficiently thick barriers, the implied velocity exceeds the speed of light, and there is no cap. You can make the barrier as thick as you want, which means you can make the implied velocity as large as you want. 10 times the speed of light, 1,000 times, 1 billion times. The mathematics places no restriction whatsoever on how fast the particle appears to cross the barrier. The only limit is how thick a barrier you care to imagine. After the Hartman effect, Steinberg later said, that is when people started to worry. But worrying and addressing the problem are two very different things. And what the physics community did in response to the Hartman effect over the following decades was something that I think reveals more about how institutional science handles genuinely threatening results than almost any other episode I have studied. Instead of focusing the full collective intelligence of theoretical physics on resolving what the Hartman effect means, on answering the question of whether tunneling genuinely violates relativity, or whether the appearance of superluminal velocity is an artifact of how we define velocity, the field did something much more comfortable. It produced definitions. Lots and lots of definitions. Over the next several decades, physicists proposed at least 10 distinct mathematical definitions of what tunneling time means. Each one captured a different physical intuition about the tunneling process. Each one gave a different numerical answer. Each one was internally consistent according to its own logic. And none of them agreed with each other. I am going to walk you through the major ones, not because the technical details matter for their own sake, but because I think the nature of the disagreement between these definitions is the real story. The proliferation of incompatible answers is not a sign that physics is closing in on the truth. It is a sign that the question itself may not have a unique answer within the current framework of quantum mechanics. The first definition, and the one that causes the most trouble, is the phase time, also called the group delay. This is the definition Hartman used. It was derived originally by Eugene Wigner in 1955 and applied to the tunneling problem by Hartman in 1962. It measures the delay of the peak of the transmitted wave packet relative to the peak of the incident wave packet. It is the most straightforward definition, the one that most closely corresponds to the naive question of if I time the particle going in and time it coming out, how long did the trip take? It is also the definition that predicts the Hartman effect and implies superluminal velocities. It is the definition that scares people, and for good reason. The second major definition is the dwell time. This was formalized by Felix Smith in 1960 and developed further by Marcus Buttiker in 1983. The dwell time approaches the problem differently. Instead of tracking the peak of the wave packet, it asks a statistical question. How much probability is inside the barrier at any given moment, and how does that compare to the rate at which probability is flowing in? In more physical terms, it asks what fraction of the particle is inside the barrier right now. This sounds more grounded than the phase time, more connected to the physical reality of where the particle actually is. But it has a problem that turns out to be surprisingly difficult to fix. It averages over all particles that encounter the barrier, both the ones that successfully tunnel through and the ones that bounce back, and it cannot separate the two. If you want to know the tunneling time specifically for particles that made it through, the dwell time cannot tell you, because the decomposition into transmitted and reflected components turns out to depend on how you do the decomposition, and there is no unique way to do it. The third definition is the one that eventually became experimentally measurable, and it is worth understanding in some detail because it is the definition Steinberg used in the landmark 2020 experiment. This is the Larmor time, first proposed by a Soviet physicist named Baz in 1967 and refined by Buttiker in 1983. The concept is elegant. You apply a weak magnetic field that exists only inside the barrier region. A particle with spin passing through that magnetic field will precess. Its spin axis will rotate. The amount of rotation depends on how long the particle was exposed to the field. So you prepare the particle's spin in a known orientation before it enters the barrier, and you measure the spin orientation after it exits. The difference tells you how much precession occurred, and from that, you can calculate how long the particle's internal clock was ticking while it was inside the barrier. This sounds like the perfect experiment, an internal clock carried by the particle itself, ticking only when inside the barrier, reading out automatically when the particle exits. But the Lama time has a feature that I think is one of the most deeply unsettling results in all of quantum mechanics, and it receives almost no attention outside specialist circles. The Lama clock yields not one, but two time parameters. One is associated with the precession of the spin in the plane perpendicular to the magnetic field, and the other is associated with a rotation in the plane parallel to the field. In 1987, Sokolovsky and Baskin showed that these two parameters are not two independent measurements. They are the real and imaginary parts of a single complex valued time. Let me make sure you understand what that means. The time has an imaginary component. The square root of -1 appears in the answer to the question, how long did the particle spend inside the barrier? If I asked you how long your commute took this morning and you answered 23 minutes plus 11 I minutes, where I is the square root of -1, you would probably back away slowly. You would be right to. That answer does not correspond to anything in human experience. We do not know what imaginary time means as a physical duration. We do not know how to interpret it. And yet, that is what the most careful theoretical analysis of the Lama clock produces. Sokolovsky himself acknowledged that this result has long caused unease. It should cause unease. It should cause more than unease. Then there is the Boettger-Landauer time, introduced in 1982, which takes yet another completely different approach. Instead of asking how long the particle spends inside the barrier, it asks a question about the barrier itself. How fast can the barrier change before the tunneling particle notices? If you oscillate the barrier height at some frequency, there is a critical frequency above which the tunneling probability starts to depend on the oscillation. Below that frequency, the particle tunnels through the barrier as if it were static. Above it, the particle starts to feel the changes. The inverse of that critical frequency is a timescale, and Boettger and Landauer argued it is the physically relevant tunneling time. This definition gives a finite, real-valued answer that does not exhibit the Hartman effect, but it also does not correspond to any kind of traversal duration that you could point to and say that is how long the particle was inside. There are more. Bohm trajectory times derived from David Bohm's pilot wave formulation of quantum mechanics. Feynman path integral times that average over all possible paths through the barrier. Various conditional time distributions that attempt to select only for particles that successfully tunneled. At least 10 definitions in total. I am not going to catalogue all of them, because the details would require a graduate course in quantum mechanics to fully appreciate. What matters is the big picture, and the big picture is this: 10 definitions, 10 answers, no agreement, and no principled way to choose between them. And here is where I need to correct a misconception that I have seen in several popular science articles about this topic, because it is widespread, and it is wrong, and it matters. The misconception is that the tunneling time problem is fundamentally a measurement problem, that physicists just have not built a good enough experiment yet, that with sufficiently clever apparatus, the question will be settled and one of the 10 definitions will be proven correct. That is not what is going on. The issue is not experimental. The issue is structural. It is built into the mathematical framework of quantum mechanics itself. In quantum mechanics, every physical quantity that you can measure corresponds to a mathematical object called a Hermitian operator. Position has an operator. Momentum has an operator. Energy has an operator. Angular momentum has an operator. You can ask quantum mechanics how to measure any of these things, and it will give you a precise, unambiguous answer. But time does not have an operator. Time in quantum mechanics is a parameter. It is the independent variable, the label on the x-axis, the background against which measurements happen. It is not itself something the theory knows how to measure. Wolfgang Pauli proved this formally in 1933, 5 years after tunneling was discovered. He showed that no self-adjoint time operator can be conjugate to a Hamiltonian that is bounded from below. In non-technical language, as long as your physical system has a lowest possible energy state, which every real system does, you cannot construct a proper quantum observable for time. The proof is mathematically airtight. It has been challenged by some of the most brilliant theorists of the last 90 years, and it has survived every challenge. This is a deeply strange situation when you step back and think about it. Quantum mechanics can tell you exactly where a particle is, how fast it is moving, how much energy it has, what its spin orientation is. It can predict the outcomes of measurements with a precision that sometimes exceeds 11 decimal places. It is, by any standard, the most accurate predictive framework ever constructed by human beings. And yet, when you ask it the simplest conceivable question about duration, how long did this event take? The theory's answer is, I do not have a way to formulate that question. Not, I do not know. I cannot even ask. What Pauli's theorem means for the tunneling time problem is devastating. It means that quantum mechanics is not merely unable to answer the question, how long did the particle spend inside the barrier? It means the theory does not contain the mathematical machinery needed to formulate the question as a well-posed observable. The theory is not refusing to answer because we are phrasing the question wrong or because our experiments are not sensitive enough. The theory is unable to answer because the concept of a duration of time spent in a region is not a quantity that quantum mechanics recognizes as measurable in the same way it recognizes position or momentum as measurable. Eli Pollack of the Weizmann Institute captured the depth of this problem in a single sentence. It is part of the general problem of what is time, and how do we measure time in quantum mechanics, and what is its meaning. Grace Field of Cambridge was even more direct. Orthodox quantum mechanics, she wrote, is not well posed to answer the tunneling time question, because doing so requires assumptions about definite particle trajectories that the Copenhagen interpretation explicitly denies. Asking how long the particle spent in the barrier presupposes that the particle was in the barrier, which presupposes that it followed a definite trajectory through the barrier, which is exactly the kind of statement that the dominant interpretation of quantum mechanics refuses to make. I have been reading about this topic for longer than I probably should admit, and I personally think this is the most underrated crisis in modern physics. Not the flashiest, not the most discussed at dinner parties or in popular science books, but the one whose roots go deepest. The tunneling time problem is not a loose thread you can safely ignore while the rest of physics carries on. It is a thread that, if you pull it honestly and follow it to its end, unravels the relationship between quantum mechanics and time itself. And the fact that this thread has been visible since 1932, while generating almost no public attention, compared to the measurement problem or the interpretation wars, or entanglement and non-locality, tells you something important about what the physics community considers comfortable to discuss and what it does not. But the story did not stay theoretical forever, because in the 1990s, a series of experiments dragged the tunneling time problem out of the seminar room and into the laboratory. And the results were, depending on your tolerance for existential vertigo, either extraordinary or catastrophic. It started at Berkeley in 1993. Ephraim Steinberg, then a graduate student working with Raymond Chow, designed an experiment to measure the tunneling time of individual photons passing through a multi-layer dielectric mirror. The mirror acts as a photonic barrier, the optical equivalent of the rectangular potential barriers in the textbook Tunneling Problem. Steinberg and Chow generated pairs of photons using spontaneous parametric down conversion, a process where a single high-energy photon splits into two lower-energy photons that are correlated in time. They sent one photon of each pair through the barrier and the other through free space of equal optical path length. Then they compared arrival times at their detectors using a Hong-O-Mandel interferometer, which provides the sub-wavelength timing resolution needed to detect differences of just a few femtoseconds. The result was clean and startling. The tunneled photon arrived first, not by a lot, but unambiguously and repeatably. The measured group velocity inside the barrier was 1.7 times the speed of light, plus or minus 0.2. Superluminal. The photon that passed through the barrier got to its detector faster than the photon that traveled through empty space at the speed of light. Steinberg and Chow were meticulous in their published language. They noted carefully that this was a measurement of group velocity, not signal velocity. The group velocity describes the motion of the peak of the wave packet, not the motion of its leading edge. The leading edge, which is the part that carries genuine information, always travels at or below the speed of light. No one can use this effect to send a message faster than light. No one can use it to violate causality or signal backward in time. The Steinberg-Chow result is compatible with special relativity in the strict sense that no information propagates superluminally. But that careful distinction, while correct, does not actually answer the question that everyone wants answered. It explains why tunneling cannot be used to build a faster-than-light telephone. It does not explain what the particle is doing inside the barrier. It does not explain why the peak of the wave packet genuinely arrives before it should. Something real and measurable is happening faster than light inside that barrier. Calling it a group velocity rather than a signal velocity is a correct categorization, but it is not an explanation. The mystery is untouched. And then Gunther Nimtz took the situation and detonated it. Nimtz was a professor of physics at the University of Cologne, and he had been running tunneling experiments with microwaves since the late 1980s, where Steinberg and Chow worked with single photons and femtosecond timing. Nimtz worked with classical microwave pulses and macroscopic apparatus. His approach was less subtle, but far more dramatic. In 1992, he reported superluminal tunneling of microwave pulses through a waveguide section narrowed below the cutoff frequency, which acts as a barrier for electromagnetic waves. But his most provocative experiment came in 1994, in collaboration with Horst Eichmann at Hewlett-Packard Laboratories. Nimtz took the audio signal of Mozart's 40th Symphony in G minor, frequency modulated it onto an 8.7 GHz microwave carrier, and sent it through a photonic barrier 114.2 millimeters long. On the far side of the barrier, he demodulated the signal. The music was there, it was recognizable, it was audible, and the measured group velocity through the barrier was 4.7 times the speed of light. He had transmitted Mozart at nearly 5 times the speed of light. I actually laughed the first time I read about this experiment. Not because it is funny exactly, but because of the sheer theatrical audacity of it. You have to understand the context. In the world of academic physics, when you get a result that seems to challenge special relativity, the expected protocol is to publish it cautiously, surrounded with caveats, present it as a curiosity requiring further investigation, and wait nervously for the community to tell you where you went wrong. Nimtz did the opposite of all of this. He spent the next 2 decades explicitly and loudly arguing that his experiments constituted a genuine macroscopic violation of special relativity. He published paper after paper, gave conference talk after conference talk, and called his critics STR crusaders, STR being the special theory of relativity, accusing them of deploying unphysical assumptions to explain away his data. In a professional culture where disputes are conducted through carefully worded footnotes and polite letters to editors, Nimtz was picking fights in the parking lot. He was not alone either. Other experimental groups had found similar results. In 1995, Spielmann, S.I. Pokes, Stingel, and Krauss in Vienna used optical pulse tunneling through dielectric mirrors and also observed superluminal group velocities. In 2007, Nimtz and Stahlhofen pushed further, claiming to have demonstrated what they called a macroscopic violation of special relativity, using microwave tunneling through paired prisms in frustrated total internal reflection geometry. This particular claim drew a sharp response from Winful, who published a direct comment arguing that the experiment was measuring stored energy release, not signal propagation. The back and forth between Nimtz and Winful became one of the longest-running public arguments in modern physics, stretching over a decade and generating dozens of papers. What makes this particularly interesting, and what I think gets lost in the technical details, is that both sides were right about their own claims, and neither side fully addressed the others. Nimtz was right that the measured group delay was superluminal. The numbers are not in dispute. Winful was right that the group delay does not represent a traversal time. The mathematical analysis is sound, but neither explanation answers the question that started all of this. What is the particle doing inside the barrier? How does it relate to time? The Nimtz-Winful debate consumed 2 decades of argument and produced a consensus about what tunneling is, not without producing a consensus about what tunneling is. The physics establishment responded with a mixture of irritation and genuine concern. Several groups attempted to identify where Nimtz's reasoning went wrong. The most thorough, and I think the most intellectually honest of these responses, came from Herbert Winful at the University of Michigan. In a landmark 2006 review paper that synthesized decades of theoretical work, Winful proposed a fundamentally different interpretation of what the tunneling group delay actually measures. Winful's key insight was this: the group delay measured in tunneling experiments is not a transit time. It is not measuring how long the particle took to cross the barrier. It is a lifetime. Specifically, it is the time required for energy stored in the evanescent standing wave inside the barrier to leak out and be detected. Here is the physics behind this. When a wave packet hits a potential barrier, most of it reflects, but some of it penetrates into the barrier as an evanescent wave. an exponentially decaying field that does not propagate. This evanescent wave is not a traveling wave. It does not carry energy forward through the barrier the way a light wave carries energy through space. Instead, it forms a standing wave pattern that stores energy in the barrier region, much like a resonating cavity stores electromagnetic energy. This stored energy then leaks out, both forward through the far side of the barrier as the transmitted wave, and backward from the near side as part of the reflected wave. The group delay in Winfall's interpretation measures the time for this stored energy to be released. The Hartman effect then has a clean explanation. As you make the barrier thicker, the evanescent wave decays further and further inside the barrier. Beyond a certain thickness, the evanescent field at the far end has already reached its minimum value. The barrier is essentially opaque past that point, and adding more thickness does not change the energy distribution near the entrance. Since the stored energy near the entrance does not change with barrier width beyond this point, the release time does not change either. The saturation of stored energy explains the saturation of group delay. There is no superluminal propagation because there is no propagation at all. The evanescent wave is the non-propagating solution to the wave equation. Dividing the barrier width by the group delay and calling the result a velocity is a category error. You are dividing a length by a time and getting a number with the units of velocity. But neither the numerator nor the denominator corresponds to what we normally mean by distance traveled and time elapsed. Steinberg offered a vivid analogy to make this concrete. Imagine a 20-car train leaving Chicago for New York. At every stop along the way, the last car is detached and left behind. By the time the train arrives in New York, it is only 3 cars long. The center of the shortened train has shifted dramatically forward compared to where the center of the original 20-car train would have been. If you calculated the velocity of the center of mass, you would get a number that exceeds the speed of any individual car. But no car was accelerated beyond the speed limit. The train was not sped up, it was shortened. The peak shifted forward because the back was removed, not because the front moved faster. This explanation was elegant, physically intuitive, and widely accepted. The mainstream consensus crystallized around it. The group delay is not a transit time. Tunneling does not involve propagation through the barrier in the ordinary sense. Evanescent waves are not traveling waves. Special relativity is safe. But the consensus was not quite as airtight as it appeared, and even its strongest proponents knew it. Steinberg himself, the person who provided the train analogy and whose 1993 experiment had launched the experimental era of tunneling time measurement, acknowledged its limits in a statement that I think is one of the most important and underappreciated things anyone has said about this problem. I do not feel like we have a completely unified way of thinking about it, he admitted. There is a mystery there, not a paradox. A paradox has a resolution waiting to be discovered. A mystery might not. The consensus explains why tunneling does not violate relativity. It does not explain what the particle is doing during tunneling. It does not explain how long the particle spends in the barrier. It does not reconcile the 10 competing definitions of tunneling time. The consensus is a statement about what tunneling is not, dressed up with sufficient authority that it is easy to mistake for a statement about what tunneling is. And then 2020 arrived, and the mystery deepened. Steinberg had spent 27 years thinking about tunneling time since his 1993 photon experiment. By 2020, he was a full professor at the University of Toronto, and he had built what is probably the most sophisticated tunneling time apparatus in existence. The experiment was designed to realize the Gamow clock concept that theorists had proposed in the 1960s and 80s. The idea of using a particle's own spin as a clock inside the barrier, an idea that had seemed like a pure thought experiment for decades, was finally going to be built and run. The setup was extraordinary. They began with rubidium-87 atoms, cooled to approximately 1 nanokelvin, roughly 1 billionth of a degree above absolute zero. At these temperatures, thousands of atoms collapse into a single quantum state, called a Bose-Einstein condensate, where they behave as a coherent quantum entity rather than a collection of individual particles. This condensate was guided along a one-dimensional optical waveguide, a channel of light that confines the atoms to motion in a single direction, like quantum marbles rolling along a quantum groove. At a specific point along this waveguide, a barrier was waiting. It was created by a blue-detuned laser beam, a wall of light 1.3 micrometers thick that repels the rubidium atoms. In classical terms, the atoms did not have enough energy to cross this light wall. But because they are quantum particles, some of them tunneled through. The key innovation was the clock mechanism. Each atom's spin state was prepared in a superposition, a quantum combination of spin up and spin down. Inside the barrier region, Raman laser beams coupled these spin states, driving precession at a precisely known frequency. The spin precesses at a rate proportional to the time the atom spends inside the barrier. By measuring the spin state of atoms that successfully tunneled to the other side, Steinberg's group could read out the accumulated precession angle, and from that, calculate how much time the atom's internal clock had ticked while inside the barrier. Ramon Ramos, the graduate student who led the day-to-day experimental work, later described the historical weight of what they were doing with a kind of awed understatement. They were just coming up with crazy ideas of how to measure this time, and thought it would never happen, he said, referring to the generations of theorists who had proposed thought experiments that nobody expected to actually be performed. The headline result, published in Nature in July 2020, was 0.61 milliseconds, plus or minus 0.07. Tunneling was not instantaneous. After 88 years of silence, avoidance, and 10 competing definitions, someone had finally put a number on it. Quantum tunneling is not instantaneous, physicists show, announced Scientific American. The question that had been open since MacColl's 1932 paper appeared to have an answer, but the paper contained results that the headlines missed, and those results were far more important and far more troubling than the headline. First, Steinberg's group found that atoms with lower incident energy spent less time inside the barrier, not more time, less. In classical physics, if you throw a ball more slowly at a tunnel, it takes longer to pass through. A car driving 30 miles per hour takes longer to cross a bridge than a car driving 60. This is so intuitive, so deeply embedded in every human experience of motion and duration that it barely requires stating. But in quantum tunneling, the relationship is inverted. Slower particles tunnel faster. The less energy you give the particle, the less time it spends inside the barrier. A 2021 follow-up paper by David Spearings and Steinberg refined the measurement to 0.59 milliseconds, plus or minus 0.02, and confirmed this counterintuitive pattern. They also found that atoms facing higher barriers spent less time inside them. The thicker the wall, the less time the particles spent in transit. The taller the wall, the less time the particle spent in transit. Every classical intuition about duration and traversal was running in reverse. Think about what that means in practical terms. If you want a particle to spend the least possible time inside a barrier, you should make the barrier as tall and thick as possible and send the particle in as slowly as you can. The optimal strategy for minimizing transit time is to maximize the difficulty of the crossing. This is not just counterintuitive. It is the exact opposite of everything that makes sense in the macroscopic world we evolved to understand. Second, and this is the part that I think has received far less attention than it deserves, the Steinberg result is specific to the Lama clock definition of tunneling time. It measured one particular quantity, the precession of an internal spin degree of freedom, and reported it with admirable precision. But the phase time, the dwell time, the Boudica-Landauer time, and all the other definitions remain separate and unreconciled. Measuring one does not resolve the disagreement between all 10. It adds a data point to one definition while leaving the others untouched. Third, and perhaps most destabilizing of all, the Steinberg result flatly contradicted a measurement published in Nature just 1 year earlier by a completely different group using a completely different method. In 2019, a team at the Australian Attosecond Science Facility at Griffith University, led by Satya Sainad, used a technique called an attoclock to measure tunneling time in hydrogen atoms undergoing strong field ionization. The attoclock works like this. You hit an atom with a very short pulse of circularly polarized laser light. The rotating electric field of the laser acts like the hand of a clock, sweeping around once per optical cycle. An electron that tunnels out of the atom exits at a particular angle relative to the field's orientation, and that angle tells you the timing of the tunneling event. The offset between the expected angle and the measured angle encodes any time delay associated with the tunneling step. Sainad's team measured this angular offset in hydrogen, the simplest possible atom, and found an upper limit on any tunneling delay of just 1.8 attoseconds. 1 attosecond is 1/100000th of 1/10000000th of 1 second. To give you a scale comparison, 1 attosecond is to 1 second, as 1 second is to roughly 31.7 billion years, which is more than twice the current age of the universe. Their result was consistent with tunneling being instantaneous, zero delay within experimental uncertainty. So now you have 2 experiments, both published in Nature, both carefully designed, both peer-reviewed, both replicated, and they disagree by approximately 15 orders of magnitude, 15 factors of 10. One says 0.6 milliseconds. The other says less than 2 attoseconds, consistent with 0. To get a feel for what a disagreement of 15 orders of magnitude looks like, imagine 2 people measuring the distance from New York to Los Angeles. One of them reports 3,000 miles. The other reports the diameter of a single hydrogen atom. That is a discrepancy of about 15 orders of magnitude. That is the scale of disagreement between the 2 most precise tunneling time measurements in history. This is not experimental error. This is not noise in the data. This is not one lab making a mistake that the other caught. These 2 experiments are measuring fundamentally different physical quantities and calling both of them tunneling time. The attoclock measures when the electron appears outside the barrier relative to the peak of the rotating laser field. The Lama clock measures how much the atom's internal spin precessed while it was inside the barrier region. These two questions sound like they should give similar answers. They do not, because they are not the same physical question. And quantum mechanics, because it does not have a time operator, provides no canonical way to determine which question is the right one to ask. There may not be a right one. The concept of a single, unique, unambiguous tunneling time may itself be a relic of classical thinking that the quantum world has no obligation to provide. Daniil Sokolovsky, the same physicist who showed that Lama time has an imaginary component back in 1987, offered what I believe is the only truly honest assessment of this situation that anyone has given. The controversy, he said, if you wish to call it that, goes to the very heart of the quantum theory and must be accepted rather than resolved. Must be accepted rather than resolved. A working physicist is telling you, in a published paper, that this is not a puzzle waiting for a clever solution. This is not a problem that will yield to better experiments or smarter theorists. This is a structural feature of quantum mechanics itself. The theory does not contain the answer, because the theory does not contain the question. But here is where everything escalates, because if tunneling's relationship with time is genuinely undefined, if the theory that describes tunnelling cannot tell you how long the process takes, then we do not understand any physical phenomenon that depends on tunnelling. And the list of phenomena that depend on tunnelling is much, much longer than you were ever taught. Let me start with the most immediate one. The reason you exist. The reason any of us exist. The reason the sky is not permanently dark. The core of the sun burns at approximately 15 million Kelvin. That sounds enormously hot. And it is, but it is not hot enough. At 15 million Kelvin, the average kinetic energy of a proton in the sun's core is about 1.3 thousand electron volts. 1.3 keV. The Coulomb barrier between two protons, the electromagnetic energy wall created by the repulsion of their identical positive charges, is roughly 1 million electron volts, 1 MeV. The protons in the sun have approximately 1/1000th of the energy they would need to overcome the barrier classically and fuse. Without quantum tunneling, fusion in the sun's core would require a temperature of approximately 40 billion Kelvin, more than 2,000 times hotter than the sun actually is. At the sun's real temperature, according to classical physics, fusion is not just unlikely, it is impossible. The protons simply do not have the energy to get close enough to feel the strong nuclear force that would bind them together. Classical physics says the sun cannot burn. Classical physics says no main sequence star can burn. The night sky in a classical universe would be black. Tunneling bridges this gap, but just barely. Each individual proton-proton collision in the sun's core has a probability of resulting in fusion of approximately 1 in 10 to the 28th power. That number is so small, it defies comprehension through normal analogies, but let me try one anyway. If you flipped a coin and needed to get 10 to the 28th heads in a row, the expected number of attempts would exceed the number of atoms in the observable universe. The improbability is not just astronomical, it is supra-astronomical. An average proton in the sun's core, bouncing around at 15 million degrees, colliding with other protons billions of times per second, waits approximately 9 billion years before it successfully tunnels through the Coulomb barrier and fuses with another proton. 9 billion years. That is roughly twice the current age of the sun. The proton-proton chain that powers our star works only because there are approximately 10 to the 57th protons in the core, each making billions of collision attempts every second. It is probability by overwhelming numbers. The most consequential process in the solar system, the furnace that drives every ecosystem on Earth, operates on odds that would be laughable in any casino. Arthur Eddington, who championed the idea of stellar nuclear fusion before anyone had the physics to explain how it was possible, was told by critics that the sun simply was not hot enough for hydrogen nuclei to fuse. His response is one of my favorite lines in the entire history of science. We tell them to go and find a hotter place. He was right about the fusion. He had no idea tunneling was the reason it worked. And it is not just the sun. Every main sequence star in the observable universe, every one of the roughly 200 billion trillion stars that populate the galaxies visible from Earth, burns because of tunneling. The red dwarf stars that make up 75% of all stars in the Milky Way burn so slowly that their proton-proton fusion rate is even lower than the sun's, their cores even cooler, and their dependence on tunneling even more complete. A red dwarf like Proxima Centauri, the nearest star to our solar system at 4.2 light-years away, has a core temperature of only about 4 million Kelvin, roughly a quarter of the sun's. The probability of any individual fusion event is lower still, and the star compensates by burning so slowly that its projected lifetime is trillions of years, hundreds of times longer than the current age of the universe. These stars will be burning long after every sun-like star has exhausted its fuel, and every second of that incomprehensibly long burn is powered by tunneling. At the other extreme, the most massive stars in the universe, blue supergiants 50 or 100 times the mass of the sun, burn through their hydrogen fuel in just a few million years because their cores are hot enough, around 40 million Kelvin, that the tunneling probability is much higher. But even they are not hot enough for classical fusion. Even at 40 million Kelvin, protons lack the energy to classically overcome the Coulomb barrier. The fusion still requires tunneling. It just requires less of it. From the smallest red dwarf that will outlast the cosmos, to the largest blue supergiant that will die in a supernova explosion in a few million years. Every star in existence is a tunneling engine. So every photon of sunlight that has ever touched your skin, every photon that grew, every plant that fed, every animal that built every civilization, every photon from every star that has ever burned in the history of the universe originated from a quantum tunneling event, a process whose temporal properties are, according to the most precise experiments and the most careful theoretical analysis available, undefined. But the implications of tunneling go further than stars. They go into your body, into the molecule that stores the instructions for making you. In 1963, a Swedish physicist named Per-Olof Lodin proposed something deeply unsettling about DNA. The hydrogen bonds that hold the two strands of the double helix together connect specific base pairs through protons sitting in potential wells. Adenine bonds to thymine, guanine bonds to cytosine, and the hydrogen bonds that connect them are maintained by protons in specific positions. Lodin proposed that these protons could quantum tunnel from their normal position to an alternative position called the tautomeric form. The tautomeric form changes the chemical identity of the base. If this tunneling happens at the wrong moment, during DNA replication, the base pair is misread. Guanine, which normally pairs with cytosine, suddenly mimics adenine and pairs with thymine instead, a point mutation, a permanent error in the genetic code, created not by radiation, not by chemical damage, not by a copying error in the replication machinery, by a proton slipping through a barrier that classical chemistry says it cannot cross. Watson and Crick themselves had speculated about tautomeric mutations in their original 1953 paper, the one that described the double helix for the first time. They recognized that if protons shifted position, the base pair logic would break, but they did not identify a mechanism. Lodin provided the mechanism: quantum tunneling. For decades, this idea was considered speculative, interesting but unproven, and possibly unprovable given the difficulty of isolating quantum effects in the warm, wet environment of a living cell. Then, in 2002, a team led by Louis Slocum, Marco Sacchi, and Jim Al-Khalili at the University of Surrey published a rigorous calculation in communications physics that changed the conversation entirely. Using an open quantum systems approach that properly accounted for thermal decoherence, for the molecular vibrations and the water molecules and all the noise of a cellular environment, they calculated the tunneling contribution to proton transfer in guanine-cytosine base pairs. Their finding was that the quantum tunneling contribution was several orders of magnitude larger than the classical over-the-barrier hopping rate. The probability of finding a proton in the tautomeric state was 1.73 times 10 to the negative 4. That sounds like a small number, and by everyday standards, it is. But let me put it in context. Your body copies 3.2 billion base pairs every time a single cell divides, and your body performs approximately 3.8 million cell divisions per second. That means roughly 12 quadrillion base pair copies per second, each one a fresh opportunity for a proton to tunnel into the wrong configuration and generate a mutation. At a tautomeric probability of 10 to the negative 4, the numbers are large enough to matter. Large enough, potentially, to contribute meaningfully to the baseline mutation rate that drives both evolution and cancer. And here is what makes this connection to the tunneling time problem more than academic. The rate at which protons tunnel between tautomeric states depends on the tunneling probability, which depends on the shape and height of the potential barrier between the two proton positions. If tunneling time is related to barrier properties in the counterintuitive way Steinberg's experiments suggest, with higher barriers producing shorter tunneling interactions, then our models of how quickly these tautomeric transitions happen may be fundamentally miscalibrated. The mutation rate that evolutionary biologists use to calibrate molecular clocks, to date the divergence of species, to estimate how long ago humans split from chimpanzees, that rate may have a quantum mechanical component that we cannot currently model correctly because we do not understand the temporal dynamics of the underlying tunneling process. The history of life on Earth may be entangled with a physics problem that has been unsolved since 1932. Judith Klimman at UC Berkeley has shown that this is not an accident. It is not a bug in the machinery of life. It is a feature. Her decades of work on enzyme catalysis has demonstrated that many enzymes achieve their extraordinary reaction rates not despite quantum tunneling but because of it. Enzymes dynamically compress their active sites, physically squeezing the donor and acceptor atoms to within about half an angstrom of each other, the distance at which hydrogen tunneling becomes efficient. The evidence is in the kinetic isotope effects. When you replace hydrogen with its heavier isotope deuterium in these enzymatic reactions, classical chemistry predicts the reaction rate should slow by a factor of roughly 7 because the heavier isotope is harder to move over the energy barrier. In some enzymes, the rate slows by a factor of 80. In soybean lipoxygenase, the isotope effect is so large that it cannot be explained by any classical or semi-classical model. It is the unmistakable signature of quantum tunneling. Your body's chemistry does not merely tolerate tunneling as an occasional glitch. It has been engineered by 4 billion years of evolution to exploit it. And if the biological implications are not enough to convince you that the tunneling time problem matters, consider the technological ones. Tunneling is not just a curiosity of fundamental physics. It is the operating principle of devices you probably use every day. The scanning tunneling microscope, invented by Gerd Binnig and Heinrich Rohrer at IBM Zurich in 1981 and awarded the Nobel Prize in 1986, achieves resolution below 1/100th of a nanometer by exploiting tunneling's extreme sensitivity to distance. A sharp conducting tip is brought within angstroms of a surface, and electrons tunnel across the gap. Because the tunneling current depends exponentially on the tip surface distance, even sub-angstrom changes in height produce measurable current variations. This instrument can image individual atoms. It can manipulate them. It has enabled the entire field of nanotechnology. Flash memory, the storage technology in every phone and laptop and USB drive on the planet, programs and erases data by tunneling electrons through an oxide layer roughly 10 nanometers thick. Every photo you have saved, every document you have stored, every app on your phone sits in memory cells that read and write information by forcing electrons through barriers they classically cannot cross. The tunnel diode, invented by Leo Esaki in 1957 and recognized with the Nobel Prize in 1973, was the first electronic device to exploit tunneling deliberately. Brian Josephson predicted in 1962 that superconducting electron pairs could tunnel through a thin, insulating barrier, a prediction that earned him the Nobel Prize in 1973 and that underlies every superconducting quantum computer built today. The 2025 Nobel Prize in Physics was awarded to Clark, Deverett, and Martinis for demonstrating macroscopic quantum tunneling in Josephson junction circuits. Work that proved tunneling is not just a microscopic oddity, but a phenomenon that can govern the behavior of macroscopic, engineered systems. But tunneling also imposes limits. As transistors shrink below about 5 nanometers in channel length, electrons begin tunneling directly from the source terminal to the drain terminal through the channel material itself, bypassing the gate that is supposed to control them. This leakage current, driven by quantum tunneling, is one of the fundamental barriers to continued miniaturization of computer chips. Moore's law, the decades-long trend of exponential growth in computing power, is running into a wall built from the same physics that makes the computing possible in the first place. Tunneling giveth, and tunneling taketh away. And in both cases, it does so on a time scale that we cannot define. And still, we have not reached the bottom. Because tunneling's implications extend beyond stars and DNA and technology. They extend to the boundaries of space-time itself. In 1999, Molik Parikh and Frank Wilczek published a paper titled Hawking Radiation as Tunneling that reframed one of the most celebrated results in theoretical physics. Hawking radiation, the faint glow of particles emitted by black holes, had been understood since Stephen Hawking's original 1974 calculation as a consequence of quantum field theory in curved spacetime, involving the creation of virtual particle-antiparticle pairs near the event horizon. But Parikh and Wilczek showed that it could be re-derived more simply and with important corrections by treating it as quantum tunneling. A particle inside the event horizon tunnels through the gravitational potential barrier and appears outside. It is the same fundamental physics as Gamow's alpha particle escaping a uranium nucleus. The same exponential suppression, the same probabilistic slipping away, but the barrier is not the Coulomb potential of a nucleus. The barrier is the curvature of space-time around a black hole. This matters for a reason that goes beyond theoretical elegance. Parikh and Wilczek's tunneling derivation contains corrections to the perfectly thermal Hawking spectrum that the original 1974 calculation did not include. These corrections mean the radiation is not exactly thermal. It is slightly non-thermal in a way that could, in principle, encode information about what fell into the black hole. This bears directly on the black hole information paradox, one of the biggest unsolved problems in theoretical physics. If information is encoded in the tunneling process through which Hawking radiation is emitted, then properly understanding that process requires properly understanding tunneling, and we do not properly understand tunneling. We cannot even agree on how long it takes. And then there is the implication I have been circling since the very beginning. The one I hinted at in the opening when I mentioned the ground state of reality. The implication that makes everything else feel like a warm-up exercise. In 1980, Sidney Coleman and Frank DeLucia published a paper that analyzed what happens if the vacuum state of the universe, the lowest energy state of empty space, is not actually the lowest possible state. What if we are sitting in a false vacuum, a local minimum of the energy landscape with a lower energy true vacuum available on the other side of a potential barrier? Coleman and DeLucia showed that quantum tunneling could trigger a transition to the true vacuum through a process called bubble nucleation. A microscopic region of space would spontaneously tunnel to the lower energy state. The boundary of this bubble, a domain wall between the false vacuum and the true vacuum, would then expand outward at the speed of light. Everything the bubble touches would be converted to the new vacuum state. New constants of nature, new physics, new rules for how matter and energy behave. Coleman and DeLucia's description of what this would mean for the contents of the universe remains among the most chilling passages in the history of physics literature. Vacuum decay, they wrote, is the ultimate ecological catastrophe. In the new vacuum, there are new constants of nature. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it. Not darkness, not emptiness, something else entirely. Something that does not include atoms as we know them, molecules as we know them, or any configuration of matter that could support anything we would recognize as structure, let alone life. The expanding bubble would not destroy you. Destruction implies a process that takes time. You would simply cease to be, replaced by new physics that has no place for anything made of the particles and forces that constitute you, and you would never see it coming. The boundary of the bubble moves at the speed of light. By the time the light from the approaching bubble reached your eyes, the bubble itself would already have passed through you and everything around you. There would be no warning, no observation, no moment of awareness, just a boundary moving at the speed of light, behind which everything that was is now something else. When CERN measured the mass of the Higgs boson at approximately 125 giga-electronvolts in 2012, that specific number, combined with the precisely measured mass of the top quark, placed our universe disturbingly close to the boundary between vacuum stability and metastability. The error bars on the current best measurements straddle the boundary line. We might be in the true vacuum, absolutely stable, permanent, or we might be balanced on a ledge, With a lower energy state available on the other side of a quantum barrier, we might be living on borrowed time, with a probability, however minuscule, that a bubble of true vacuum will nucleate somewhere in the observable universe and begin expanding toward us at the speed of light. The tunneling probability for vacuum decay, if our vacuum is metastable, is estimated to be extraordinarily small, something like 10 to the negative hundreds per year per observable universe volume. The expected lifetime of our vacuum state would be incomprehensibly long, perhaps 10 to the power of hundreds of years, far exceeding not just the current age of the cosmos, but any timescale that has physical meaning. We are not in any practical danger, but the calculation that produces this reassuring number is a tunneling calculation. It uses the same tunneling framework for which we have 10 mutually incompatible definitions of time. It relies on the same mathematics that predicts the Hartman effect and implies superluminal velocities. It employs the same physical process that Steinberg's lab showed behaves in ways that invert every classical expectation about duration and traversal. We are estimating the probability of the most consequential possible event in the history of reality using our single most poorly understood quantum process. And we are doing it within a theory that has been mathematically proven unable to answer the question of how long that process takes. I want to come back to the people now, because I promised earlier that the lives of the physicists who discovered tunneling were marked by a strange and painful irony. And I think understanding what happened to them illuminates something important about why the tunneling time problem stayed invisible for so long and why it continues to receive far less attention than it deserves. George Gamow tried to escape the Soviet Union twice before he succeeded, and both attempts were the kind of thing that would be rejected as implausible in a screenplay. In 1932, 4 years after his tunneling paper, he and his wife Lyubov Fokmintseva, whom everyone called Ro, attempted to kayak across the Black Sea from Crimea to Turkey. 250 kilometers of open water in a folding kayak. They packed eggs, chocolate, and 2 bottles of brandy, which is the supply list of either a very optimistic physicist or a deeply desperate one. They paddled for 36 hours before a storm forced them to turn back. Gamow later wrote that he would never forget the sight of a porpoise seen through a wave illuminated by the sun sinking below the horizon, which is the kind of thing only a physicist would notice while fleeing a totalitarian state. In a kayak, a second attempt from Murmansk toward Norway through the Arctic also failed, driven back by wind and currents. Both escape attempts went undetected by the Soviet authorities. This was either miraculous luck or a sign that even the NKVD had difficulty keeping track of a 2-meter-tall Ukrainian with cartoon drawings on his academic papers. His actual escape came through the 1933 Solvay conference in Brussels. Niels Bohr arranged for Gamow's invitation. Getting exit visas from the Soviet government required Gamow to insist that his wife come too, which was nearly unprecedented and aroused immediate suspicion. Marie Curie personally intervened at the conference to help prevent the Soviets from forcing the Gamows to return. They never went back. If Gamow had not escaped, he would almost certainly have been destroyed. His close friend, Matvei Bronstein, a brilliant theoretical physicist who was among the first to work on quantum gravity, was arrested in 1937 and executed in 1938 at the age of 31. The charges were fabricated. Lev Landau, another close colleague and one of the greatest physicists of the 20th century, was arrested in 1938 and spent a year in the NKVD's Butyrka prison before Pyotr Kapitsa convinced Stalin to release him. The purges consumed an entire generation of Soviet scientists. Gamow got out through a combination of Bohr's influence, Curie's intervention, and the kind of luck that makes you wonder about probability distributions. He spent the rest of his career in America, first at George Washington University and then at the University of Colorado in Boulder. His contributions are so broad, they seem impossible for a single person. He co-developed the liquid drop model of the atomic nucleus with Bohr. He applied nuclear physics to stellar evolution and calculated the rates of thermonuclear reactions in stars, work that directly built on the tunneling probability he had derived as a 24-year-old in Göttingen. He was one of the first to propose what we now call the Big Bang theory of the origin of the universe, arguing that the universe began in a hot, dense state and expanded, a model that was mocked by Fred Hoyle, who coined the term Big Bang as a put-down that accidentally became the standard name. Most remarkably, he predicted in 1948, with his students Ralph Alpher and Robert Hartman, that the Big Bang should have left behind a residual cosmic microwave background radiation with a temperature of approximately 5 Kelvin. This prediction was confirmed in 1965 by Arno Penzias and Robert Wilson, who detected the radiation accidentally while testing a microwave antenna at Bell Labs. The measured temperature was 2.7 Kelvin, close to Gamow's prediction. Penzias and Wilson received the 1978 Nobel Prize. Gamow did not. He was reportedly devastated by the omission. He died in 1968 of liver failure at the age of 64, having never received the Nobel for any of his contributions, including the tunneling paper that solved alpha decay, the Big Bang model, or the prediction of the cosmic microwave background. Any one of these, taken alone, would have been a worthy Nobel. Together they constitute one of the most productive careers in the history of physics, and the Swedish Academy never recognized it. Edward Condon, co-author of the Gurney-Condon tunneling paper, was destroyed by something even more senseless than the Soviet purges. He was destroyed by American fear. Condon was born in Alamogordo, New Mexico, which would later become famous as the nearest town to the Trinity nuclear test site. He was one of the founding members of the Manhattan Project, personally recruited by Robert Oppenheimer to serve as his associate director at Los Alamos. He later left the project for personal reasons and became director of the National Bureau of Standards and president of the American Physical Society. He was, by any measure, one of the most accomplished and respected physicists in America. Then the House Un-American Activities Committee came for him. HUAC chairman J. Parnell Thomas called Condon one of the weakest links in our atomic security. J. Edgar Hoover, FBI director, labeled him nothing more or less than an espionage agent in disguise. Both accusations were completely baseless, later shown to be constructed from rumors, guilt by association, and deliberate misrepresentation of Condon's attendance at routine scientific conferences where Soviet scientists were also present. Condon had committed the crime of being a physicist during a period when any international scientific contact was viewed with suspicion. His security clearance was questioned in 1948, revoked, restored after review, and then revoked again. Richard Nixon, then a junior congressman on HUAC, personally took credit for one of the revocations. New York University offered Condon a prestigious department chairmanship, then rescinded the offer under political pressure. he eventually found a position at Washington University in St. Louis, then moved to the Joint Institute for Laboratory Astrophysics at the University of Colorado. But the damage was done. Frederick Seitz, who knew Condon well, observed that he was never again quite the same cheerful, carefree man. The irony here is so heavy, it is almost physically uncomfortable. Edward Condon proved mathematically that particles can penetrate barriers thought to be impenetrable. He showed that the walls of a nuclear prison are not solid, that what appears to be an absolute barrier is at the quantum level permeable. And then he spent the last decades of his career unable to penetrate a barrier of political paranoia built by men who could not have passed an introductory physics exam. The man who understood better than almost anyone alive that apparent walls are not always real was stopped by a wall made of nothing but fear and ignorance. Ronald Gurney met a grimmer fate still. He was English, described by those who knew him as extremely shy with a characteristic English reserve. He was brilliant, co-authoring not only the alpha decay paper with Condon, but also fundamental work on the electrochemistry of ionic crystals and the theory of electronic semiconductors. After working in the United States for many years, he became entangled in the periphery of the Klaus Fuchs espionage investigation. Not as a participant, not as a suspect in any meaningful sense, but through distant professional connections from his time at Bristol, where Fuchs had also worked. The FBI investigations were enough to poison his career in the atmosphere of McCarthyite terror that pervaded American academia in the early 1950s. He lost positions at Columbia, Johns Hopkins, and the University of Maryland. Each time, the pattern was the same. An offer would be made and then quietly withdrawn after the background check came back with the FBI's notations. Gurney died of a cerebral hemorrhage in 1953 at the age of 54. Professionally devastated. His obituary in Physics Today was brief and understated, far shorter than his contributions merited. The man who wrote that the alpha particle slips away almost unnoticed, himself slipped away from the history of physics almost unnoticed. His co-discoverer of one of the most important results in 20th century nuclear physics died in obscurity during the peak of McCarthy's influence. His career destroyed, not by scientific failure, but by political hysteria. I do not think there is a conspiracy here. I want to be completely clear about that. I am not suggesting that the tunneling time problem was deliberately suppressed by a shadowy cabal of physicists who knew the truth and decided to hide it. That is not how science works, and that is not what happened. But I do think there is a pattern worth naming explicitly. Institutions, whether political or scientific, have a deep and consistent tendency to avoid confronting implications that threaten their foundational assumptions. McCarthyism could not tolerate ambiguity about loyalty. The boundaries of acceptable thought were drawn, and anyone who fell outside them was punished. The Copenhagen interpretation of quantum mechanics has its own boundaries of acceptable thought, and the tunneling time problem falls outside them. Asking how long did the particle spend inside the barrier presupposes that the particle was inside the barrier, which presupposes that it followed a definite trajectory through the barrier, which is exactly the kind of statement that the Copenhagen interpretation, the dominant interpretation of quantum mechanics since the 1920s, explicitly and categorically refuses to make. The question is not merely unanswered within the standard framework. It is, in a very real sense, improper. Asking it means you have already committed to a picture of reality that Copenhagen rejects. This is why Grace Field's observation cuts so deep, and why I have not been able to stop thinking about it since I first read it months ago. Considering the amount of hand-wringing over spooky action at a distance, she wrote, surprisingly little fuss has been made about superluminal tunneling. She is exactly right. And the asymmetry is extraordinary once you see it. Entanglement and non-locality have generated Bell's theorem, the aspect experiment, the Gamow experiment, multiple Nobel Prizes, an entire quantum information industry worth billions of dollars, dozens of popular science books, countless magazine articles, at least one major Netflix documentary, and decades of heated philosophical argument. The tunneling time problem, which touches equally fundamental questions about time, causality, locality, and the completeness of quantum mechanics, which has been open for longer than the entanglement debate, which has direct experimental evidence of superluminal group velocities confirmed across multiple wave systems, has received in comparison 10 incompatible definitions, a handful of specialized review articles, and a collective shrug from the wider physics community. Why does one foundational problem get an entire cultural industry while the other gets a footnote? I think the answer is uncomfortable but honest. Entanglement has a comfortable ending. Bell's theorem tells you the universe is non-local, but it also tells you that no usable information travels faster than light. It is spooky, in Einstein's famous word, but it is safe. You can write about it in a popular book and leave the reader feeling pleasantly unsettled, but ultimately secure. The rules of physics still hold. The universe is weird, but navigable. The tunneling time problem does not have a comfortable ending. The Hartman effect genuinely predicts superluminal group velocities. The experiments genuinely measure them. The best response physics has produced is not "this is resolved," but rather you are dividing the wrong distance by the wrong time and calling the result a velocity, which is the kind of careful definitional distinction that is correct as far as it goes, but does not actually resolve anything. It is a definitional retreat, not a solution. And the underlying mystery, what is the particle doing during tunneling? How does it relate to time? How does the process actually work at a level deeper than probability amplitudes? Remains completely open. There is no comfortable ending to hand the reader. The story does not wrap up. And stories that do not wrap up do not make good popular science books or Netflix documentaries or Nobel Prize acceptance speeches. The problem is not getting better with time, it is getting worse. In 2025, a team led by Ramona Sharo-Glazova published an experiment in Nature that probed the dynamics of photon tunneling against the predictions of Bohmian mechanics. David Bohm's alternative formulation of quantum theory that assigns particles definite positions and velocities at all times, guided by the wave function. In Bohmian mechanics, tunneling has a specific physical picture. The particle approaches the barrier, slows down as it enters the evanescent region, and eventually stops. It sits inside the barrier at rest, motionless, until the wave function evolves enough to pull it out the other side. This is the Bohmian prediction for opaque barriers, and it is testable. Sharo-Glazova's group found that tunneling photons exhibited finite dwell time and an energy-speed relationship inside the barrier that did not match the Bohmian prediction. The photons were not at rest inside the barrier. They were moving with a finite and measurable speed. This appeared to challenge one of the few interpretations of quantum mechanics that gives a definite physical picture of tunneling. A rebuttal paper was published almost immediately on the arXiv, arguing that the observable predictions of Bohmian mechanics and standard quantum mechanics are provably identical, and that the experiment could not possibly distinguish between them without additional assumptions. The debate is ongoing. No resolution is in sight, and I personally find it telling that even the attempts to resolve the tunneling time problem by switching interpretive frameworks end up generating new controversies rather than settling old ones. The problem appears to be interpretation proof. It is not that we are using the wrong framework to analyze tunneling. It is that every framework we try runs into the same wall. And then there is the result that I still do not know how to think about, even after reading everything I could find about it. Steinberg's group at Toronto has recently reported experimental evidence suggesting that, under certain carefully controlled conditions, a photon can spend what appears to be a negative amount of time as an atomic excitation during tunneling. Negative time. Not zero, which was alarming enough when MacColl found it in 1932. Not complex with an imaginary component, which was disturbing enough when Sokolovsky derived it in 1987. Negative. The particle's internal clock ticks backward. The duration it spends interacting with the barrier is less than nothing. I do not know what negative time means. I suspect nobody does. But if zero tunneling time threatened our understanding of velocity and causality, and complex tunneling time threatened our understanding of what physical quantities are allowed to be, negative tunneling time threatens our understanding of the direction of physical processes. We are running out of conceptual framework in which to even describe what tunneling experiments are finding. So here is where I am going to leave you. Not with an answer, because there is no answer. Not with a resolution, because the physics is unresolved. Not with reassurance, because nothing about this story is reassuring. The tunneling time problem was not buried because it was wrong. It was buried because it was right. And what it implied about the limits of quantum mechanics was too uncomfortable to confront in 1932. It was too uncomfortable in 1962. It is too uncomfortable now. Every decade since its discovery, new experiments have sharpened the question rather than resolving it. Every new definition has added to the proliferation rather than converging toward consensus. And every attempt to measure tunneling time directly has revealed behavior that makes the problem deeper, not shallower. Slower particles spending less time. Higher barriers producing shorter transit. Two experiments in the same journal disagreeing by 15 orders of magnitude. Complex valued durations. Negative durations. The trajectory of this problem over 97 years is not toward resolution. It is toward deeper and stranger incomprehension. And the stakes are not academic. If we do not understand what tunneling does to time, we do not fully understand nuclear fusion in stars. We do not fully understand the mutation rate in DNA. We do not fully understand how Hawking radiation encodes information from black holes. We do not fully understand the stability of the vacuum state that determines whether reality as we know it continues to exist. We are building our understanding of the most consequential processes in the universe on top of a phenomenon whose most basic temporal property has been undefined since the year it was discovered. The particle slips away almost unnoticed. That is what Gurney and Condon wrote in 1928, and they meant it as a poetic description of an alpha particle quietly escaping a nucleus. Just a literary flourish at the end of a physics paper. But 97 years later, their words read like something else, like a diagnosis, Because what slipped away almost unnoticed from the physics of tunneling was not just a particle. It was the question of what tunneling means for time. And by the time anyone noticed the question was missing, it had already burrowed into the foundations of everything we think we understand about the physical world. The calculations have been checked and rechecked for nearly a century. The experiments have been designed and redesigned and replicated across every wave system physics can access. And what they show consistently and without exception is that every time someone tries to pin down how long a tunneling particle spends inside a barrier, the answer changes depending on how you look. 10 definitions, 10 answers, no convergence, and a mathematical proof, courtesy of Wolfgang Pauli, that the theory cannot choose between them. The process that powers every star, that rewrites the code in your DNA, that determines whether the vacuum beneath reality is stable or perched on a ledge, operates in a relationship with time that our best theory of physics cannot define. That is not speculation. That is not fringe science. That is published, peer-reviewed physics. It has been saying the same thing since 1932. And the particle that slipped away almost unnoticed is still tunneling, still crossing barriers without telling us how long it takes, not because we have failed to ask the right question, but because the answer, as physics currently understands the concept of an answer, may not exist. And everything you have ever known, every atom, every star, every breath, exists because of it.